We're going to move on to studying one-dimensional motion. Keep in mind that this is strictly one dimension, forward, backward, or left or right, but not both. So we're going to discuss three topics: displacement, time, and when combining the two to compute the average velocity of a particle. Now, when we talk about particles, we are talking about the point on an object where all measurements are made. So, particles are the points on an object where all measurements are made. Now, if we're looking at a car that is racing, and we get to the finish line where the checkered flag is, and the car is going this way, we usually make that point of measurement the front. So it's when the front of the car crosses the finish line. That's the particle on the car that we're making all measurements from. This particle has to start behind the starting line, and it has to cross the finish line. Typically, though, in physics, we're dealing with not just, where a particle is moving, but also where all forces and things like that act. So typically in physics, the center of an object is where we originate our measurements from. Why might that be? Well, if we're making all measurements from this end of the object, if we happen to be going the other way, the measurements still have to be made from the back of the object. Sometimes that's sort of confusing because we have to take into account the length of the object. If we measure from the center, it doesn't really matter which way we're going. Left, right, or up and down. It's easy to find the center of anything. So we try to measure from the center of an object, unless it's specified otherwise. So that's what we mean by a particle. There's another term we need to understand called displacement. Displacement is a vector quantity that points from, I'll spell it right, point P1 to point P2. So here we have point P1. Over here we have point P2. If it's very clear that the distance between these is a straight line, and that's the distance, a vector quantity that points from P1 to P2, and it's usually measured in meters. Now, this displacement is always the same regardless of the path. So here's the vector that describes the displacement from point 1 to P2, but we could also have a path that doesn't go straight. It could go something like this. Like that. Still, the displacement is the same, because all along here we have tiny little vectors that keep changing direction. And if we look at their components, we can see that if we add all the components up, they would still equal this distance between, this displacement between P1 and P2. So here we'd have a little y component, x component. This one's all in the x, this one's all in the y. This x could cancel out this x, and eventually, if we add them all up, we'll get a distance that equals P2 and P1. So typically we call this distance delta x. Delta means change, of course, so we call that change in position x. And in this case, delta x equals P2 minus P1. So, delta x equals x2 minus x1. So the place you end up minus the place you started from. Make sure you always get that order right. It's just like in calculating the slope of a line. So we'll do a couple other examples. Let's imagine that we've got a coordinate grid, y-axis and x-axis. And we find 2 points. This one, minus 2, 0. And this point would be 4, 0. So if we had a vector that went from there to here, we could use these points to describe it. Likewise, we could have another vector that goes this way. And its coordinates could be something like, we'll call that 2, 5, and this one be 2, 1. Now, we'll call this vector A, and this is vector B. The displacement vector always equals x2 minus x1. So since we're working in one dimension here with vector A, it equals x2 minus x1. We started at minus 2, 0, so that would be, we ended up at 4, 0, so that would start at vector point 4 minus 2, where we ended up. And so therefore that displacement equals 6. It works in the y direction as well. If we look at vector B, that's going to equal y2 minus y1. We ended up at y equals 1, and we started at y equals 5. So 1 minus 5 equals negative 4. Now, if you remember from our discussion of unit vectors, we can also indicate direction with a hat. So this would be minus 6i hat, meaning positive 6 on the x-axis, and this would be minus 4j hat, meaning it's going straight down. Now, it's easy to describe vectors when they're parallel to an axis, but sometimes vectors like this might be more difficult. However, you can set your coordinate grid anywhere you like. So if, let's say, we do it like this, and we make this the x-axis and this the y-axis, we can still easily describe one-dimensional motion as being in the x or the y direction. We'll get into 2 dimensions later.